right? But the main thing that we didn't go into that we're going to go into today is how do we learn this from data, right? After all, this is our main purpose here, is to figure out how to learn these things, okay? And there are basically two main dimensions along which this problem can vary, and therefore for combinations, since each one of them has two options. So the first option is whether the structure of the network is known or unknown. Okay? So the structure of the network being known means that I already know this part. I'm just trying to figure out this part. Okay? I know who depends on what. What I haven't figured out, and the data is going to help me figure out, is how much. Okay? So this is one option, known or unknown structure. The other dimension is whether in my training data I have in each example the values of all the variables or only the values of some. Okay? We already faced this problem, or in a way a simpler version of this problem, apropos of what? Where did we look at this problem of learning with missing data?
Decision trees.
Decision trees, exactly, right? We had to figure out what to do if some examples were missing some of the values of the attributes, right? What did we do at learning time, and what did we do at inference time? And, we saw a few solutions to that problem. In all truth, those solutions were purely heuristic, right? We had no particular guarantee that they would be good. They seemed to be reasonable. The solution that we're going to learn today actually is in some ways the well-founded solution to this problem. Okay, and you'll see why and how. And in fact, one thing that you could do is, if you have your training data with missing values and you want to learn a decision tree, maybe the first thing that you should do is actually run EM to learn a Bayesian network the way that we're going to look at here, to fill in the missing data. Right? People often don't do that because it's very expensive and doesn't scale as well, but at some level that is what you should do. Okay? So we're going to look at each of these combinations in turn. Right? So first of all, let us look at the case where the network structure is known and we have complete data. Okay? So we just want to learn now the parameters of the Bayesian network. So how might you do that? Hint, this is not a trick question, and it's easier than it seems.
Just look at the data and infer the frequency with which.
Exactly, just look at the frequency with which things happen in the data. Right, remember, this is what we did when we learned naive Bayes. Right? In naive Bayes, all that we did was count how often each attribute value occurred with each class value. Right? That's all. That was all we needed to do. And if you think about it, a Bayesian network, as we saw last time, is a generalization of naive Bayes, right? So if we know how to do this for naive Bayes, then maybe we know how to do it for Bayesian networks in general. Okay? In particular, for example, let's go back to our park ranger example, right? What do I really need to do? I need to learn all these tables for all the nodes, right? But if I know how to learn each of these tables, then I'm done. And how do I learn a table? Actually, it's very simple, right? To learn the table for campfire, right, I just have to count how many times, for example, when storm is true and bus 2 group is true, what fraction of that time campfire is also true, right? And let's say I have 1,000 examples and 400 of them, I have 1,000 examples in this condition and 400 of those, have campfire equals true, then the probability is 0.4. And since these are the days of big data, let's say that instead of 1,000 examples, you have 1 billion, right? Out of which 400 million have campfire true. Doesn't this sound more impressive, right? But it's just as easy, right? It will take longer, right? But notice the time only goes up linearly with the size of the data, right? You can still do this amazing thing that is very appealing to people with large data problems of a linear scan of the data does the job for you. So what I have to do in that linear scan of the data is for each variable and for each combination of values of its parents, count how many times each value of the variable occurs. Okay? And then we're done, right? That is basically our probabilities when I divide each, for example, the number of times that C was true divided by the total number of times that S and B was true, right? And same thing for not C. I get my probabilities. Okay? Any questions? So learning Bayesian networks when the structure is known and there's no missing values is very straightforward and very fast, and this is really good. Okay? There's really no difficulty there. Okay? It's just the same ideas in naive Bayes generalized.